So, good afternoon, everyone. So lovely to see such a full lecture theatre for this, my second lecture. And as you can see, today's theme is somewhat different. We're talking about heavenly music, so the sounds of the universe. And we're going to be looking at astronomy in a completely new way. We're all used to astronomy being a visual science. It's one that's very easy for people like me who have to give talks in it. There are all these spectacular pictures, both from space-based telescopes and ground-based telescopes, and also little robotic probes flying around the solar system. However, I'm going to take a different approach today, because vision is only one of the human senses. We're going to start appreciating different aspects of astronomy through the vehicle of sound, to give us, just a new perspective on some of the phenomena and some of the processes out there in space. So, there are different ways that I'm going to use sound within this lecture. They're not all real sounds. So, the way I'm using sound, first of all, I'm using it as a diagnostic. So you can use sounds, or the presence of sounds or signals, to infer something about an object. So it could be lightning, the presence of storms and lightning on Jupiter. It could be the physical structure of the inside of the sun. I'm also going to be using sound and showing how it is an actual physical process. It's a way of carrying energy over some of the vast volumes of space. And then I'm going to be using sound as a way of representing different phenomena. So things where there's a certain pattern, or there's a change in the frequency, or there are natural radio signals. I'm going to be looking at converting them to sound so that you can better appreciate them. I could show you a lot of these phenomena as graphs, okay? Be very boring to look at. If you actually listen to it, you can pick up a lot more of the subtleties of the signal. So the whole idea of sound in space is quite a new thing in astrophysics. I mean, astronomers have long known that there is sound out there in space, but I would say it's only during the last sort of couple of decades that we've started to use it and understand it in all these ways that I'm describing. So the first thing, of course, is there is no sound in space. That's what we're always told. Well, that's not exactly true. There's no sound in a vacuum, and space is not completely a vacuum. So there will be some real astronomical sounds that I'm playing for you today. However, I must give you a warning. First of all, that out of all the real sounds that I'm going to play today, there is only one that you could hear if you were there and you were listening with your ears. There's only one that would appear as you could hear it. All the rest are at pitches that are far too low for the human ear. So to make them audible, we've had to change them by sort of speeding them up to bring them into the audible frequency range. So they don't sound quite the same as the versions I'm playing here. So even where there are real sounds, we've mainly had to change them. The second warning to give you is that many of these were never sounds in the first place. They're either, as I just told you, natural radio signals, which have been converted via a radio receiver to sound so that you can hear them, or perhaps patterns or a repetitive beat or something like that. It gives you an incidence of something happening that's been then changed to a sound so you can hear it. So just keep that flag in mind. I will try and tell you as we go through, remember to tell you about which is which. But first, I've quite blithely said there's sound in space, and I've talked about sound not carrying through a vacuum. I just want to explain a little bit about the physics of sound, because it's quite important to understand how sound can carry in space, what kind of sound can carry in space, and why we think it can carry in space. So the first thing is light, like from these stars, or whether it's visible light, X-ray light, whether it's radio signals. They're a form of what we call the electromagnetic radiation. They travel by oscillating electromagnetic fields that can travel through a vacuum. Sound is completely different. Sound needs a medium to carry it. So, for example, here's a little piston pushing on some air molecules within a tube. This is how you start a sound wave. You have some vibration, some motion that just squeezes the particles in the air together and squeezes them to higher pressure. That's what we call a compression. And then these knock onto the regions around them, squeeze them to be at higher pressure, while the original particles relax back to what we call a rarefaction. The next regions have moved to high pressure, and the signal travels on. So just the movement of the piston here, squeezing on the nearby particles, as soon as this is a rhythmic process, it sends out ripples of pressure. So if you like, a sound wave is a pressure wave. It's these signals of where things are compressed, rarefied, compressed, rarefied. And this is how sound works. It's how the sound you're hearing now works. I am expelling air from my lungs. It's traveling over my vocal cords and my vocal cords are vibrating that air. And I can change the pitch because I've got muscles that squeeze, contract, or change the shape of my vocal cords. But it's the air that carries that sound through my mouth, through the room, to you. It's all these minuscule compressions and rarefactions traveling through the air to your ear, where the particles are physically hitting the membrane, that's your eardrum, which is then converted to the signal that goes to your brain. So if you actually look at any of the particles in this simulation, just to completely mesmerize you if you haven't been looking at it for long enough, if you just identify any single one of these particles, you see it's not actually going very far. And this is a crucial thing. When I send my sound out to you, I'm not sending air particles across the room. The little particles don't go anywhere. They just sit there and they vibrate. So, for example, that was not one of the noises I'm going to be playing here. So, for example, the best way to describe this is a Mexican wave. I'm quite tempted to try and make you do it, but I think we've turned the lights down, so it might be a bit practice. But you know what I mean? It's where you stand up, put your arms down, and then it travels along the row. But just get that idea that, you know, the message moves, the signal moves, and in case of sound, that message can actually carry energy. You're transferring energy, but none of the particles are actually physically moving anywhere. So in terms of sound, we characterize it as, you know, different notes, different sounds according to their wavelength. The wavelength is the distance between successive compressions, or if we express it as a wave, between the peaks, or say the troughs of the wave. And you get all different waves of different wavelengths, both long ones and short ones. The other way we characterize waves is not so much in terms of wavelength, but particularly in terms of sound and notes, and as frequency. And some of you may remember this from your school physics. There's a nice little equation. It's the only one I'm going to show you today. But effectively, that means that if you had all these waves travelling by me, these sound waves travelling by me at the same speed, you would see that I would get a lot more of these peaks going past me a second than I have of the long wavelength peaks. So that's just telling you that if you have a very short wavelength, lots of these cycles go past you in a second, long wavelength, fewer. And so frequency is just a measure of how many of those cycles go past. And in terms of human hearing, we talk in terms of cycles per second. Our ear is very sensitive to sounds that are between about 20 and 20,000 cycles per second. But of course, that's just what we can hear. It doesn't mean that there aren't other sounds out there. I can send up sound waves very easily by flapping my arms around in the room. I'm doing exactly the same thing. I'm setting up regular compressions that are traveling through the air to your ear. However, I'm doing this far too slowly for you to pick up. It doesn't mean the sound isn't there. It's just that you can't hear it. So space is not completely a vacuum. I'm going to be showing you various places within our solar system, perhaps within a galaxy, even in between galaxies where there is matter sitting there in space. Now, they don't tend to be atmospheres in the sense that we think of the air in this room as an atmosphere or a medium. Typically, with the air, say, in a room like this, the particles, the molecules of air are separated by, they fill about 1,000th of the space in the room. The rest is completely nothing. There's a lot of space between the molecules, each separated, say, about 10 times their size. So that's a very thick atmosphere compared to the kind of environments we're talking about, space, where you're talking about molecules separated by about 10 million times their size. Okay? So it's a very sparse, thin gathering of gas, nothing like we're used to in terms of thinking about what we know, what we experiment with. But nonetheless, there are particles out there, and that means they can bash into each other and they can transmit a wave, a sound wave. So as long as you've got a medium, you can travel, you can send a sound wave through it. The challenge is, or the subtlety is, that not all sound waves will carry. And in fact, only the longest wavelength sound waves will carry through a medium that's sparsely separated. So, for example, obviously not to scale, but if this is the little molecules in our room, you only have to displace one a tiny amount before it bangs into a neighbouring molecule and it can set up that sound wave. And of course, that original displacement is what gives the frequency or the wavelength of the sound travelling. Move to outer space, again, not to scale. If you nudge one of those molecules by a tiny amount, well, it doesn't actually collide with anything. The sound wave doesn't propagate. In space, the only sound waves that can propagate are the ones that have a really large wavelength, where you're pushing and displacing things large enough that they actually collide with the next particles on. So that's why I'm saying that all these sounds that I'm going to talk about are largely inaudible, because the wavelength is far too long for us to hear. Very long wavelength, incredibly low frequency, some of these sounds. So this is why when you stand out in your back garden and watch the stars, you haven't got this cacophony of noise. It's out there, just you can't hear it. Okay, I think that's probably enough of bits of the physics for the time being. Let's go to some of the sounds. Now I'm going to start with our atmosphere. Our atmosphere is very noisy. We hear sounds all the time. Obviously, one that's very loud is the dramatic thunderclap that accompanies a lightning strike in a storm. Now, I'm not going to talk about that. That's caused by the motion of the air rushing in to fill the gap after the lightning strike. When you have storms, you have incredible releases of electric energy. And this gives off energy as light in all the wavelengths there are. So in the visible, that's what the lightning flash is. But it also gives off electromagnetic radiation right down into the radio. And this is the first of many signals, natural radio signals, that are in our atmosphere and around us all the time. If we had ears that could convert radio signals to sound, the whole of the atmosphere would be a very noisy place. So in the case of lightning strikes, if you're standing quite close to the lightning in a thunderstorm and you have a radio receiver, remember this is a radio signal, it converts to sort of little popping sounds that are just a little bit like, it sounds a bit like sort of bacon frying or twigs snapping. I know, you thought you were going to hear better sounds than that, didn't you? It's going to get better. But if you start going further away, so that's say if you're within a few hundred kilometres of a thunderstorm, you pick up those sort of cracking sounds. If you have radio receivers much further away, now some of these electrical waves, so electromagnetic waves, some transmitted down, some go up. And if you go higher up in our atmosphere, you have what's known as the ionosphere. It's an ionized layer of gas on top of our atmosphere. And if if the radio waves travel through there, because it's a charged plasma and because moving charged particles are what cause radio signals, there's a dispersion. You have a difference between different charges and how fast they move through an ionized plasma. And so if you're further away and the signal's taken longer and it's traveled through this ionized plasma, you get a difference in that the higher frequencies travel sooner or travel faster, lower frequencies arrive later. So a little bit further away, that little cracking and popping gets dispersed into what's known as a tweak, slightly more lengthier noise. But then there's an even more extreme version of this, where very rare lightning strikes where, unlike in this photo, it doesn't come down to the ground, but it goes between the clouds high up in the atmosphere. Some of this radiation is directed upwards, directly up into the ionosphere, where it travels, it gets directed along the magnetic field lines, and it's travelling huge distances. If you think of the way, the Earth is like a bar magnet with the magnetic field going around that. As soon as you get these particles moving along magnetic field lines, the radio signals are directed from the northern hemisphere down to the south, or from the south up to the north. They're travelling over thousands of kilometres. That's a long time for those signals to get dispersed in frequency. And so you have a very characteristic signal. It's called a whistler. Again, the higher frequency tones arrive earlier, and they're followed by the lower frequencies, so you get this falling, descending tone that lasts a couple of seconds. The neat thing about those is that, say in the northern hemisphere, we will get the whistlers from lightning strikes occurring in the southern hemisphere and vice versa. They've travelled all that distance in the meantime. So you may think this isn't very astronomical. Okay, we're still stuck on Earth. But of course, the Earth isn't the only place that you get thunderstorms, that you get lightning strikes. All the gas giants have got enormous storms whirling within their cloud levels. You've got this enormous hurricane here on Jupiter called the Great Red Spot, and many other smaller clouds and storms. Now, we know that deep in these storms, perhaps about 100 kilometres below those very top clouds, you've got lightning flashes. This is a picture from the Galileo spacecraft of the nighttime side of Jupiter. So there's a glow of the clouds, that's reflected light from one of Jupiter's moons onto the backside, onto the night side of Jupiter. And you can see some bright sparks here. These are some of those lightning flashes deep in the clouds. This picture was taken in the 1990s, but we knew far earlier that there were lightning strikes and storms on Jupiter, because when the Voyager probes passed by Jupiter, they had radio signals. And they detected those whistler radio signals, characteristic of those high lightning strikes in the atmosphere of Jupiter. So I'm going to play you those now. It's a very much noisier signal. There's a lot of crackle and pop, but if you listen, there's a very faint, characteristic falling tone of a Jovian whistler. And of course, you don't just generate these moving charged particles that give the radio signals here within thunderstorms within the atmosphere. There's a plentiful supply of them from outside, raining onto our atmosphere all the time in the form of what we call the solar wind. This is a picture of the sun's surface, the southern hemisphere, in UV light. And I hope you get the sense of matter streaming off away from the sun's surface. The sun is giving off this solar wind of highly charged particles all the time. It spreads out between the planets and forms the interplanetary medium, and it interacts with our atmosphere. When it does, we get the northern lights. This is a picture of the northern lights seen from the space shuttle. What happens is that those charged particles, a lot of them are deflected by a magnetic field, but some actually get funneled down, especially around the poles where the magnetic field comes in and is very much stronger. They come in, they collide with molecules of oxygen, nitrogen in the air. Those collisions are what provide this sort of luminous glow that we call the northern lights. But those charged particles, again, moving through a magnetic field, they also create a natural radio signal. So when you see aurora, again, very low frequency receivers can turn the sound, turn those signals to sound. So this is the sound of aurorae here on Earth. And there are all kinds of other signals. There's one called the dawn chorus, which sounds like little birds. Instead of that sort of noisy chatter, it's little birds tweeting. You get all these kind of radio signals for the interaction from the solar wind and our magnetic field. But again, it's not just the Earth that has a strong magnetic field. It's not just the Earth that experiences a solar wind of particles. If we look at Jupiter and Saturn, they both have aurorae around their poles. Here they're shown it's sort of superimposed on an optical image. They actually shine in the UV because you're fluorescing hydrogen to produce the glow for the Jovian northern lights. And also on Saturn, round the pole here, very strong auroral signals. Now, last lecture I talked about the Cassini spacecraft flying around Saturn. It also has a radio receiver, and there are some very complicated interactions between the solar wind and the magnetic field, the magnetosphere of Saturn. And here are some of the radio signals of the aurorae on Saturn transcribed to sound by the Cassini instrument team. So I hope it's beginning to sound a bit more spacey now, yeah? Yeah. Now, one of the things that Cassini had to do when it arrived at Saturn was it had to maneuver itself into the right orbit and around where it wanted to go in the system. And as part of this maneuvering, it had to actually cross through the ring of the planes twice. And sensibly, if you're going to fly little spacecraft through the rings of Saturn, which are full of tiny particles, you choose a nice gap, like here. But of course, that gap isn't completely empty. They had to fly through that gap twice. And what it did is it turned, you can see it's got a radio receiver here, this big sort of dish. It actually turned that in front, so it acted like an umbrella as a shield as it moved through the rings, because those gaps are not completely empty. And this little spacecraft is plowing through at 20 kilometers per second. What has been done, though, is every time one of those little particles, tiny particles of dust that occupy the gap in the rings, hits the antenna, it records a signal by the onboard instruments. And it's been turned to a sound. So and now you're hearing the rate of hits on that antenna as the spacecraft goes through the rings. Obviously, it gets loud as it goes through the center and then tails off again as it moves away from the rings. So the fact that it doesn't last that long tells you how thin the rings of Saturn are, remember. You're probably only a few hundred meters at most, and if you're going through at 20 kilometers per second, you go through very fast. So the actual signal doesn't last long, but at the peak, you're looking at just short of 700 hits per second on that antenna. And one of the first things that Cassini did when it got to Saturn was it released a little probe called Huygens, which parachuted down through these murky methane atmospheres of Titan to land on the surface. And there was a very simple, very clever experiment, which was they put a microphone on the outside of the Huygens space probe to record the sound of the winds of Titan as it parachuted down. Now, the whole descent lasted about 2.5 hours. I'm just going to play you about the last 30 seconds. And what you're listening to are just the sounds of the winds buffeting the little spacecraft. And this is what you would hear if you were there riding this parachute down to the ground. So this is the only real sound that I'm going to play today. The winds are travelling sort of 6 or 7 kilometres an hour. They're quite fast. And you'll hear it's quite noisy. And then as you get closer and closer to the ground, it's going to get quieter. And the moment where it dims completely is the moment that little space probe settles on the ground and the winds completely drop, because it's then sort of sheltered out of the wind. The moment that Huygens became the furthest thing that humankind has landed a space, it's the furthest thing we've landed on another body in our solar system. I mean, it's not a very sophisticated experiment. It's akin to sort of driving along in your car and just sticking a microphone out the window, okay? But you'd be surprised that it hasn't been done more often. In particular, the obvious target would be Mars. And indeed, in 1999, there was an American polar lander sent to Mars, which had exactly that, a little microphone provided by the Planetary Society stuck on the outside of the craft to record the descent and the sounds of Mars. Unfortunately, that was one of the many missions to Mars that failed. So that never worked. And apparently the Phoenix lander from a few years ago also had a microphone attached, but in the end that was turned off because it was part of a package that might have interfered with the descent process, and I think they worried at the last minute that it would affect the descent. But hopefully there are new missions to Mars planned, and one of them may contain a microphone. It will be fascinating to hear the sounds on Mars, because you have an atmosphere, it's much thinner than the Earth's, but you have sounds carried. We've got storms, we've got dust storms, we've got winds. There's a lot going on in the atmosphere. So hopefully we will soon be able to hear the sounds of Mars for ourselves through a similar experiment. So the sun, I've told you, it's the source of the solar wind. It sends all these sort of charged particles out into the solar system. It's responsible for a lot of those radio signals. But the sun itself is a source of sound, real astrophysical sound. The whole of the sun is vibrating, it's shimmering. It's got sound waves travelling all the way through the core. So just like a bell or a gong that you struck and you send it sort of vibrating and you produce the sound, it's similar with the sun. The sun is just one big ball of vibrating sound waves. And how this works is because the sun is a plasma, it's a hot gaseous body that is continually in motion. Right at the core, the core is the only place it's hot enough, sort of like 10, 15 or so million degrees for nuclear fusions to occur. That's where the energy is produced in the sun. The material above that core gets heated. Heated things rise. It rises up, then it cools, and then it falls back down. And we set up convection cells within the outer layers of the sun. And this is just a sort of very narrow part of light on the sun, just showing a close-up of some of the tops of these convection cells. If you imagine if you're looking at water boiling in a pot, you see that kind of seething, that bubbling. You're just looking at a top view down on those. And each of these represent large rivers of plasma coming up and then sinking, these convection cells. Except, of course, that this is the sun. This is on a big scale. Each of these is, perhaps a couple of 1,000 kilometers across. These are giant convection cells. So the sun is in motion, and what happens is that because you have a gaseous atmosphere, because you have motions, you set up sound waves travelling through the surface. In practice, these sound waves are generated on the inside of the star. And this is an important difference between, say, like the bell or the gong ringing and what happens in the sun. From there, you hit the outside and the outside vibrates. Here, the sound waves come up, they hit the inside of the sun and then get reflected back down. Now, this is how we can detect them. All of this is in motion. Here's a picture just of those motions of the sun, those boiling of the convection cells that are going on all the time. Now, each of these motions are setting up sound waves that then hit the surface and cause the surface to oscillate in and out. And if things are moving towards and away from you, then you get a signal of that in what's known as the Doppler effect, the Doppler shift. It just changes the colour, the spectrum of the light emitted slightly. And so we have Dopplerograms that look at the motions of the surface of the sun. So these are the turbulent motions from the plasma. This is the surface of the sun oscillating inside and out. And it's oscillating in and out because of all the sound waves hitting it and being reflected. Okay, so sound waves through the sun. This is an interesting concept. This is the best way we have of actually seeing what the physical structure of the inside of the sun is like. It's a very complicated body. The physical structure changes, the properties change as you go deep inside the sun. Now, obviously, it gets hotter, it gets denser. Those properties tend to affect things like the sound speed, so the rate that the sound waves travel through the sun. So if you have sound waves generated under the surface, they tend to be directed down into the sun. And then depending on which direction they go, they experience very different physical conditions within the sun. So for example, sound waves like this blue one that travel right through the centre of the sun go where it's hottest and the sound speed is fastest. Ones that are directed into more shallow regions of the sun rattle around much more quickly, because what happens as the sound speed changes, you get a refraction. The sound waves never reach the core of the sun, but they get slowly bent away by the increase in the sound speed to come back to the surface again to be reflected back. And so you have different, we call them resonant modes. There are different established patterns within the sun where these build on each other. So you have very short wavelength, high frequency sounds that sample the outside of the sun, whereas the very low frequency notes sample the inside of the sun. And you've got all these different sounds happening at once. There aren't just, how many of that is 4 different notes that the sun sounds. It's a lot more complicated than that. But why we use them is we use these as diagnostics of of the sound speeds at the different layers in the sun and the different conditions in the sun. So for example, if I have 2 very slightly different frequency sound waves, I've got a yellow one that rattles around higher, and I've got a green one, slightly longer frequency, that just samples a slightly lower patch of the sun. So the difference between the properties of these 2 sound waves tells me, differences in their frequency, tells me something about the physical properties within this layer of the sun, because it's related to the sound speed, which is then related to these other properties of the sun. So if I have all these different frequencies, and I can disentangle which frequencies sample which regions of the sun, then I can begin to start building up a picture of how the sound speed and therefore how other properties change within the sun. And there's a huge industry. This is called helioseismology. So in the same way that seismologists might use the vibrations within the Earth to tell something about the Earth's interior, we can use the vibrations of the sun to tell something about the interior of the sun. Now, as I said, there aren't just 5 or 4 sounds. There are probably of the order of 100,000 oscillations within the sun, resonant frequencies. So this is an incredibly hard job to disentangle which are the resonant frequencies, which sample which depths. And, you then compare it to theoretical modelling, models on a computer that you build up. You have your structure of the sun. What sound waves would you predict? How does that compare to the ones you observe? And so the observations feed into theory, feed into the observations. However, this does mean that the whole of the sun is humming. You can't hear it because it is a true sound, but it is much, much lower frequency than we can hear with our ears. So, for example, I'm going to play you a sound from the SOHO satellite, which detects these oscillations in the sun. But because it's such a low frequency, we've had to speed it up a bit. So we're compressing, it's about 40 days worth of recordings into a few seconds. So it's speeded up by about 40,000 times. And again, we're just picking out a few of the resonant frequencies in the hum of the sun. Of course, the sun is just a star, and there are many, many other stars in the sky. Now, the sun is the easiest star to study because it's the next one to us, it's bigger and brighter. We're looking for sort of oscillations, tiny oscillations, periods of about 5 minutes or so on the sun. The motions are a matter of centimetres per second, they're not very fast. It gets a lot more difficult to do this with more distant stars. The more recent breakthrough, though, has been with missions such as Kepler. Now, Kepler is a little spacecraft. It's orbiting out in space, and it's looking for exoplanets. It's looking for planets around other stars, and it does this by monitoring the brightness of those stars, and it's looking for a regular signal of a planet silhouetted in front of it, and that's how you tell the stars there. But one of the byproducts, a fantastic byproduct of this mission, is that you're continually monitoring the brightness and the surfaces of all these stars. And you can see changes in the brightness according to some of the dominant resonant frequencies within the stars. And so for the last sort of 30 years or more, we've been doing helioseismology. More recently, we've moved to astroseismology. Again, it's the only way we have to sample the inside of these stars. Temperature and brightness are easy to measure from the colour and the luminosity of the star. But actually knowing what's going on within the core is a lot more difficult. And this is the only way we can do it at the minute. And the advantage is, of course, that we can do this for stars that are similar to the sun, so how typical is the sun perhaps, and then to stars that are very different. So I'm going to show you, just play you again some of these sounds, very much speeded up, but the hums of different stars. Now we're going to start off with one that's very similar to the sun. It's a similar age, it's slightly hotter, slightly more massive, slightly brighter. It's called Alpha Centaurus A. It's one of the closest stars to us. And its beat sounds like this. So not that really different from the sun. But then maybe we choose one that's slightly younger than the sun, even bigger in temperature and radius. And this is HD 49933, the hum from this star. It's got quite a good sort of Doctor Who feel about it, isn't it? And then, of course, there are ways of sampling, not just with Kepler, but with some of the best ground-based telescopes. Again, very nearby, very bright stars, looking, again, motions on the surface, looking for that Doppler effect, and disentangling the resonant frequencies to give you the sound. Now, here, I'm going to play you one from a very large star. It's something of the order of 10 times the size. It's probably about 60 times brighter, 3 times more massive than our sun. It's much, much younger. It's a star in a completely different stage of its life. It's a very different kind of star to our sun. And it has much longer period vibrations because it's bigger, it takes longer for the sound waves to travel through it. And so, whereas on the sun, maybe the average period is about 5 minutes, here we're looking at much longer periods of a few hours. And this has got a really good syncopation going to it. I think they may have cheated and just done that on a loop to get the syncopation. So all the stars in the night sky are really humming, real sounds that we can't hear. There are some even more extreme stars out there, and in fact, there's one just up here in that kind of area. And this is associated with the core of this nebula. This is the oh, great, I like it when somebody says, wow. Nice picture. I know we're doing the sounds, but it's nice to have good pictures as well. So this is the Crab Nebula. It's the remains of a star that exploded about 1,000 years ago. This is what big stars do at the end of their lives. They throw off the outer layers in the supernova explosion. The central core collapses under gravity. It's no longer producing energy at the core. It can no longer resist the lure of gravity to pull it in. And it gets more and more compressed, the core of the star, and it gets squeezed to such a point that atomic nuclei break down. Electrons and protons get squeezed together to form neutrons, and you end up with this big ball of neutrons. Now, at this stage, as long as it's not, say, more than 20 times more massive than the sun, it can stop the inward pull of gravity, because neutrons don't like to be squeezed. They've got what we call a degeneracy pressure. They don't like to be pushed too close together. They exert an outward pressure that resists the inward pull of gravity. At that point, the gravitational collapse stops, and you have what's known as a neutron star. So you have something that was originally, say, a few million kilometres across, squeezed right down to something about the size of London, 10 kilometres across. So it's got a lot more compact. It's so compact, if you took a teaspoon of neutron star material, it would weigh about 1 billion tonnes. Okay, so that really is compact. Not just that, as it's got squeezed down, anything that was rotating originally, like stars rotate, as they squeeze down, they spin up. Think of the ice skater drawing in her arms. She spins up faster. Stars do the same thing. Well, figuratively. As they shrink down, they spin up. Not just that, but any magnetic fields that were laced through that star get much more concentrated. And so neutron stars are spinning very rapidly. Not just that, but some of them produce, they've all got these really strong magnetic fields. And sometimes we actually see manifestations of these called pulsars. So imagine you've got a very strong magnetic field. Around the neutron star, you have what's known as a magnetosphere. I mean, do you have a layer where you've just got charged particles, things which aren't neutrons, but electrons and protons just surrounding it? Now, the effect of charged particles, very strong magnetic field, it actually it has the effect of funneling them outwards in very tight beams directed along the neutron star's poles. So you have these twin beams of radiation. You get light, you get very strong radio signal along these beams. And you see them if they happen to sweep across in front of you. So imagine this neutron star spinning very fast. Of course, the magnetic field might be misaligned from the way it's spinning, so the beam sweeps around like this, like a lighthouse beam. And if it happens to just clip in front of you, you get a pulse of radiation every time the star rotates. Of course, there are plenty of neutron stars out there where maybe the beam's not directed across our point of view. We never see it as a pulsar. The pulsars are just the one where we actually clip this beam. So here is a radio signal. I mean, I could show it to you in light, but the kind of speeds we're talking about, this flickering, they're too fast to detect with the eye, but you can hear the differences if we convert each of those pulses to a sound. So this very first pulsar is one of the brightest ones known. It was the first to be discovered. It rotates at about 1.4 times a second. So you can hear the audible, again, you can hear very distinct pulses. Okay, if we go to the one at the centre of the Vela supernova remnant, it's a lot faster, about 11 times a second. Okay, now this is the Crab one. Sorry, I got them in the wrong order. This Crab one is a lot faster. It's now spinning at 30 times a second. Where's my mouse? That isn't as fast as they get. We have a whole branch of millisecond pulses. This one spins at 174 times a second. I can do better than that. Here's one at 642 times a second. Ooh, it's a bit loud. But the key thing about those is every time one of those clips goes past, that's how the neutron star's rotated once. Just think, something the size of London rotating 642 times a second. Okay? That means the outer layers of that star are travelling at a seventh the speed of light. That should give you an indication of how strong the gravitational field is in that neutron star, that it doesn't just disintegrate and fly off into space, that it's still being held together as a coherent body. So, if gravity wins and things collapse, there gets a point, if you've got something more massive than a neutron star, you can't withhold gravity, can't resist gravity. Gravity keeps collapsing down, and you get extreme objects called black holes. And the most massive black holes are found sitting in the most massive galaxies in the whole universe, and these are found in the centres of clusters of galaxies. Now, this is what you would see in a cluster of galaxies if you have a very good optical telescope. You just see all the stars in all the galaxies, and they're of the order of, hundreds to thousands of galaxies within a volume of a few million, say tens of millions of light years across. Okay, it sounds big, but it's small. Very dense concentration of galaxies. Trouble is, when you look in the visible, you don't see all the ordinary matter that's there. In between the galaxies in the cluster, there is an atmosphere. I'm going to colour it purple in this next image. There's 10 times more matter in between the galaxies than there is in the galaxies. You just don't see it because it's very hot. It's at millions of degrees. You need an X-ray telescope to see it. And in fact, if you looked at this cluster in X-rays, you wouldn't see the individual galaxies. All you see is a big puddle of million-degree gas. So here is an intra-cluster medium. You have an atmosphere, very hot atmosphere, sitting between the galaxies in the cluster. You have an atmosphere, you can put a sound wave through it. So we have an interesting sound wave this is how I originally got interested in this area of astronomy, is by studying this cluster of galaxies. This is the Perseus cluster. It's one of our nearest rich clusters. It's only 250 million light years away. And this is the largest galaxy right at the core, NGC 1275. Now, of course, these are the visible galaxies. In between all of these, you've got the hot X-ray gas. So if I zoom in around that galaxy, you see it's kind of a weird galaxy anyway. Right at the centre, it's got a supermassive black hole. If I move to X-rays, you can see the gas that lies outside the galaxy. Remember, you no longer see the galaxy because it's too cool. So if you look at X-rays, you're only seeing really hot things. You're seeing the gas in between the galaxies. Now, obviously, it extends way out beyond this image, down the floor, up to the ceiling, out to the sides, as a smooth atmosphere. I'm just interested around the central cluster galaxy because it's corrugated, it's got structures. You don't see the galaxy, but you see bright light here at the core, and that's issued from the vicinity of the black hole, the supermassive black hole in the galaxy. You can also see cavities in the gas. These are big bubbles in the gas. But the structures that I'd like you to notice in particular are perhaps faint ripples you can see. It's not really apparent on this. Instead, I'm just going to change the contrast a little bit to bring them out. It's just a little bit of tweaking to bring out very low surface brightness features. And you can see there are ripples in the gas. And the way X-rays work, if you have higher densities, you produce more X-ray emission. So where you get brighter ridges, that's where material is denser, it's being squeezed together. Where you've got dimmer regions, that's where it's not so dense. So this sounds familiar. Regions of compression and rarefaction mirrored in the X-ray light. So what we have here is a sound wave. And we think it's caused by the black hole at the centre. Not all the matter that spirals down into a black hole actually gets accreted. It's only about 10% of fission. There's a lot of matter and there's quite a lot of energy that never quite makes it down the black hole. It's something to do with the way you've got magnetic fields spinning very fast. You have twin jets of emission and charged particles blasted out the poles of the black hole. Now, these are physical jets of plasma. And what happens is they come out and they plough into this space. They go through the galaxy, blast their way through the galaxy, and then they hit this intercluster medium. Now, of course, we're seeing something like here, disturbance at the centre, setting up concentric ripples. Though, it's not happening on a timescale that we can see like this. What we effectively have is a snapshot where you see the ripples and you can infer there's been a regular disturbance on such and such a period at the centre. So the jets from the black hole come out, push aside, sweep aside the X-ray cluster gas, sets up these ripples. And in fact, when you look at the ripples, they are quite regularly spaced. Distance between those ripples gives you the wavelength. You can have a good guess for the sound speed within this gas because we understand plasmas and different temperature gases. You can work out a frequency of this note. And I can tell you with great authority, because I'm on the paper, it's a B-flat note. But it's not a B-flat note that you're used to. I mean, we're used to sounds that are cycles per second. This is one cycle every 10 million years. So this is an extreme note. Astronomy is the physics of the extreme. And this is what we think is the deepest note in the universe. It's quite a pure note because that's a regular wavelength. And, it got picked up by the press here. Black hole things. Happy black. In fact, the only thing I think my sons have ever been proud I've done here is an entry in the Guinness Book of World Records for the deepest note in the universe. I mean, this is a silly side to it, but there's a very serious side to this, of course, because all this gas is hot. Why does it stay hot? If it's giving off energy in the form of X-rays, it should be cooling down. The fact that it's still hot means that energy is ploughed into it in some way. And these sound waves are a mechanism from energy released around the, accretion energy around the black hole, making it out via the jets into the intercluster medium. So the jets, the energy is then transferred to pushing on the gas. You have the sound waves can then distribute this energy throughout the intercluster medium where it dissipates as heat. And so these sound waves are a way of actually keeping the gas very hot and connecting what's going on in the intercluster medium to what's going on right in the central black hole. It's the equivalent of something like a size of a marble, as if we scaled it all down, influencing a whole area the size of an Earth. It's just that connection, the way the energy is transported is through the sound waves. So the final sound I'm going to play you and talk about is quite a fundamental one that is very important for every single one of us because it's had a role to play in shaping the galaxies, all the structures, clusters of galaxies that we see in the present-day universe. And we have to go back to the very earliest light of the universe. This is the cosmic microwave background. So effectively, The early universe was a hot soup of charged particles. You know, it's very tiny, very hot, it's very bright. You've got charged particles flying around, you've got lots of photons of light. The problem is that the photons of light are trapped. They can't escape. They can't get any distance, for they interact with the other particles. And so we can't actually see this early universe because none of the photons escape away from us. The difference happens at about 380,000 years into the universe. Well, the universe, you know, is growing and it's cooling down. At that point, it suddenly reaches a temperature where the charged particles are cool enough that they start to combine into atoms. Then they stop interfering with the photons, leaving the photons to stream towards us. So the first light we see is at that point when the photons are released and they can then travel across the universe towards us. This is a picture of the microwave background. I'll explain what the colours are in a minute. This is a picture of the whole sky. You know, so you've got a globe that's just been unwrapped and laid flat to give you this shape. So when you look at this, it's like looking almost at the underside of a cloud. It's about the best analogy I can come up with. When you look at clouds, you know that way above there, there's the sun. There's a huge source of energy. The photons, you don't see the photons directly from the sun. You just see the ones that make it out from the underside of the cloud. So you have a very good picture of the underside of the cloud. It's effectively the same with the cosmic microwave background. It's the edge of a fog that obscures the early universe. Now, I said I'd explain the colours. It's microwave background because obviously it's stretched and it's cooled so much since the beginning of the universe. It's now at temperatures only about 2.7 degrees above absolute zero. It's mainly all the same colour, and there are just minute variations, about 1 part in 100,000th in temperature. And this is a temperature map. So red gives you, so they've subtracted out the average and they're just giving the fluctuations above and below. Red is warmer, blue is cooler. And denser regions are warmer. So this is also a measure of where there are compressions and enhancements in the density across the whole of the microwave background of the universe at that instant. It's like a snapshot of the outside of that cloud. It gives us a snapshot of what the universe was like at that time. And some of these density enhancements are where things are close together and gravity's pulling them together. Now, dark matter, which says, everything in the universe is more or less dark matter. You have an awful lot of dark matter, it responds very quickly to gravity, and it starts to clump. Ordinary matter is a bit more complicated. It doesn't just respond to gravity, it's also got things like pressure, Coulomb forces. It kind of fusses around a bit before it settles down and it collapses under gravity. So while it's rattling around and bouncing, it's colliding with each other and it's setting up sound waves within the plasma of this early universe. So when you look at these density enhancements, some of them are due to obviously matter beginning to be slightly closer together and collapse under gravity. Some of them are also provoked by sound waves oscillating through the early universe. And some of these sound waves go on and provoke collapses of structures at certain intervals, because these tiny little seeds over densities are where gravity starts to run away, it carries on, and you start to grow some of the shapes of the first galaxies. So this is the very tracing, the very beginnings of some of the structures we see in the early universe. And of course, astronomers study this as like the beginning conditions, and then you run a model universe in your computer and see whether you end up with a universe like we see today. So the last sound I'm going to play you is some of these sound waves in the early universe. Now, obviously, that's just a snapshot. What Mark Whittle at the University of Virginia has done is he's taken, obviously, he can measure the wavelength of these sounds. The universe is expanding. Space gets stretched. That means the wavelength of these sounds gets stretched as well. And so you're going to hear a falling tone. The picture's going to fall, and it's going to be the first million years of the universe, okay, compressed into 10 seconds. So, this is speeding it up by 100,000 billion times, okay, so this really is about, as low as you can get. And it's the noise of just how those compressions stretch as the universe grows. Yeah. Okay, so this has been a bit of a gallivant through some of the many sounds of the universe. I will say there are plenty more that I didn't get a chance to include, especially some of the natural radio signals. You can access all the sounds and the original web pages from the different research groups via this web source, which is also in the transcript that will be outside. And just to say that we're going to take a break now, but I will be back in February, where we can go back to some of those ideas of rotation, of neutron stars, maybe of Saturn's rings from last lecture, and I'll be talking about all different facets of rotation in astronomy on Wednesday the 1st of February. Thank you.